Okay, it's a pleasure today to have Charlie Kane from University of Pennsylvania for today's colloquium. This is one of the few times, one of the only times when we have a colloquium speaker who's talking about the field that he invented, that he developed, right? Which is now one of the most interesting fields, popular fields in condensed matter physics. Charlie got his PhD at MIT. He went to IBM. I don't think he went to Santa Barbara, did he?
No,
But
just
he
for
worked
visits.
with Matthew, I guess,
Starting
at IBM. He did work in spin Hall effect, but the thing that he's really known for that's taken off is topological matter and topological insulators. He's won several prizes for that. He's won the Buckley Prize, he won the Dirac Medal, I guess it is, and the European Physical Condensed Matter Physics Prize. And what he's going to tell us about today is not only the hard condensed matter version of this, but he and one of my former colleagues, Tom Levinsky, figured out a way that you could do this with soft matter. So it's everything in condensed matter. Charlie?
Okay, well, thank you very much. Thank you very much. It's really a pleasure to visit here. And so, so this talk is going to be a little bit of a experiment for me. This is the first time I've tried this. And so I'm going to start off telling you the story of topological insulators. And so this is a story in its own right. But what I would like to tell you after giving you the elements of this is that the ideas that go into thinking about topological insulators have a much wider range of applicability, and in particular, they apply to certain systems which are of interest in soft matter and statistical mechanics, namely the mechanical modes of certain lattices which are called isostatic lattices. And so I'd like to try to explain to you this problem, and this is a problem that was really introduced to me by Tom Levinsky, and so what I'd like to argue to you is that one can understand these using the same language that we use to understand these. So that's the plan. So now over the years, you know, my work on topological insulators really started off as a collaboration with Jean Malie, and then I was joined by my students and postdocs in that work. And so the beginning of the talk is really sort of dedicated to them, but then this second half really grew out of work that I did with Tom Levinsky, who's been my inspiration at the University of Pennsylvania for over 20 years. So okay, so what I'd like to do is to start off with the idea of the insulating state. So the insulating state is really the most basic state of matter. Okay, and you know, we teach our freshmen about insulators, and we tell them that in an insulator, the electrons are bound to atoms, and so they're stuck and they can't go anywhere. Okay. Now, actually, the insulating state is a uniquely quantum mechanical phenomenon. Okay, because it comes about because of the quantization of energy levels. So the simplest kind of insulator is an insulator of inert atoms, and there you get an energy gap that separates the occupied states from the energy states and empty states, and it's this energy gap that makes an insulator electrically inert. Okay. Now, a crystal of inert atoms isn't very interesting. It gets more interesting when you bring them together and let the atoms interact with each other. And then they can form covalent bonds. And so the way that we have learned to describe the electronic properties of these kinds of crystals is the language of the band theory of solids. And so this was really one of the triumphs of quantum mechanics in the 20th century, was developing the language for how we can describe the electronic properties of these materials. And so this is the band structure of silicon, but let me just simplify it a little bit and to think about what a band structure is. And so in the band theory of solids, you take advantage of the symmetry of a crystal to classify the electronic states as a function of their momentum. Okay, and so you can draw the energy as a function of momentum, and for each momentum you have various energy levels which form the energy bands. Now in an insulator, there is an energy gap that separates the occupied electronic states, which form the valence band, from the empty electronic states that form the conduction band. Okay, and so this gives you it's the existence of this energy gap that gives you the essence of the insulating state. Okay? Now, there's a sense in which the insulating state that you have in an insulator, a semiconductor like silicon, is really kind of the same as the insulator that you have in an insulator like solid argon, which is just, inert atoms. Okay? The only difference is a matter of size. But you can imagine sort of, continuously dialing up the energy gap and going smoothly between this kind of insulator and this kind of insulator, and nothing really happens along the way. Okay? So there's a sense in which this insulating state is really the same phase of matter as this insulator. Now actually, it's really kind of the same as the vacuum. Because the vacuum isn't as empty as you first might have thought. At least according to Dirac's theory of relativistic quantum mechanics, the vacuum has a valence band too. Okay, so according to Dirac's relativistic quantum mechanics, the electrons are the conduction band, and the antiparticle of the electron, the positron, is the valence band. Okay, and the only difference again is a matter of scale. The energy gap here is 1,000,000 times bigger. Okay, now the idea of topology in topology in insulators is to ask the question, well, is this the whole story? Are all of these the same? Is every state that has an energy gap the same as every other state that has an energy gap? Okay, and the answer to this is no. And so states that have an energy gap fall into distinct classes, which sort of can be smoothly deformed into each other, but to go from one class to another, you necessarily have to go through a state where this energy gap goes to zero. Okay? And so this is the essence of the idea of topological band theory. And so what I'd like to do is to introduce the notion of topological band theory sort of by an example. And to give you the simplest example, this is an example of of a one-dimensional insulator. Okay, and so this is a famous model of polyacetylene. Polyacetylene is it's basically, you can think of it as a chain of carbon atoms, a one-dimensional chain of carbon atoms, which are arranged so there's basically one electron on each of the carbon atoms that's in play. Okay. And so this is a famous old problem which was really popularized by Sue Schrieffer and Heeger, who this was work back at the University of Pennsylvania long before I arrived there. So the idea is the following: that so the carbon atoms form this chain, and if all of the bonds in the chain were the same, then it would form a one-dimensional conductor, okay, with a half-filled energy band, okay? Now, but what the system would like to do is it likes to dimerize and make sort of alternate short, long bonds, okay? And by doing that, by lowering the symmetry of this one-dimensional crystal, what that does is it opens up an energy gap between the valence band and the conduction band. Okay, and by opening up an energy gap, it lowers the energy of all of the occupied states, and so this dimerized state is a lower energy configuration. Okay, and so there's an instability towards doing this. Now, so now it's an insulator. Okay, it has an energy gap separating the occupied valence band from the empty conduction band, but this is an interesting situation, because there are two ways you can do it. Okay, you can either have what I call the A phase, where I alternate short, long, or I could do it the other way around. I could do long, short, okay? And these two phases, they kind of look the same, okay? But I want to argue to you that they are topologically distinct, okay? Topologically distinct in the following sense, that the only way I can go from this to this is to go through a state where U is equal to 0, and that has the energy gap vanishes. So if I think of the energy gap as a function of the dimerization, then the A phase and the B phase are separated by a quantum critical point where this energy gap vanishes. Okay? Yeah.
Isn't the B phase just the A phase if I look at it from behind the slide?
Well, so there's certainly symmetries that relate the A phase to the B phase. But if I want to, keeping the atoms put, if I want to go from the A phase to the B phase, I necessarily have to go through this transition. Okay. So but you're right, there are symmetries in the problem which relate.
Sorry, what's the horizontal axis physically on that?
The horizontal axis
Yes.
is the dimerization. So here, what I'm doing is I'm moving the green atoms to the left by U, so U is negative. And here, I'm moving the green atoms to the right, so U is positive. And so this axis U is how much I've shifted the atoms over by. Okay. All right. So now, so I've sort of given you a picture that these two phases are topologically distinct in the sense that in order to get from one to the other, you have to sort of go outside of the insulator. Okay? And so the way we can characterize these topological phases is to borrow an idea from the mathematical theory of topology. So in mathematical theory of topology is concerned with various shapes and is asking the question what things can be deformed into each other, and what things can't. So for instance, a sphere can be deformed into the surface of a bowl. Okay? Or a donut can be deformed into the surface of a coffee cup. Okay? But you can't get from a sphere to a donut without poking a hole in it, and that's against the rules. Okay? Now the difference between the sphere and the donut can be characterized by what's called a topological invariant. Okay? And a topological invariant, in that case, is basically just counting the number of holes. So it's called the genus. So a sphere has genus 0. A torus has, a donut has genus 1, okay? And so, so likewise, the A and the B phase can also be distinguished by a topological invariant, which in this case is an integer. And the way you can think about that integer is, so if you write down a model for this, you can write down, you can think of a two-band model where you're just describing the conduction band and the valence band. So that means that for every momentum, there are only two states. And so the Hamiltonian is a 2x2 matrix. And any 2x2 matrix I can think of as like the Hamiltonian for a spin. Okay, spin up and spin down. So it has two values. And so I can think of this as some field acting on the spin. And so in this model, it turns out that this field is acting in the xy plane, okay, as a function of k. And so one can characterize this Hamiltonian as a function of k around this Brillouin zone in terms of the winding number, how many times this vector wraps around the origin. So in the A phase, it wraps around. It doesn't wrap around the origin, so the winding number is 0, whereas in the B phase it does wrap around the origin, so the winding number is 1. Okay? And so this topological, and so this gives us an integer topological invariant that distinguishes these two topological phases. Okay, so that's, yeah.
There's a symmetry, and so
Yes.
there's
Yes.
also
Yeah. I know. So you're asking if these two phases look the same by symmetry, why do they look different here?
Yes.
Okay, and the reason for that is that in defining my Hamiltonian, I had to define a unit cell, and the unit cell I defined is like this. So that unit cell, by choosing the unit cell violates the symmetry. Okay, but I had to choose a unit cell. And so I had to violate the symmetry. So that's so you're right, but I'm right too. Okay,
What if you made the unit cell consist of like 4 atoms or something? It's the same way. Even if you
well,
double the
yeah,
size of the
yeah,
unit cell, you have the same problem.
yeah. So look, so we're stuck with this. So another way you can say it is that this topological invariant that I have, there's a certain ambiguity to it, okay, which you can view as sort of a gauge ambiguity. I could do a gauge transformation which would change this winding number, okay? But the important thing though is if I compare two different states, the difference of their the difference in this topological invariant is gauge invariant. Okay, so you know, I don't want to go into too much detail, mathematical detail about this, but the main point though is that if I have different topological phases, then one can define some sort of invariant. Okay, and in this case, the invariant is an integer. Now, one thing, I put a little star here, just so there's one more caveat. So, you know, I told you this is the winding number, but of course, that assumes that this field is in the plane. Okay? If the field can tilt out of the plane, then of course I don't have a winding number anymore. Okay? But that fact is guaranteed. So in this model, it's certainly the case, and so this fact is guaranteed by a certain kind of symmetry that this model has, which is called a particle hole symmetry, and that actually guarantees that the valence band and the conduction band are sort of mirror images of each other. Okay, and so now that's actually not a real symmetry of polyacetylene, but it's a symmetry of this model, and it's actually a reasonable approximation for this model. So this gives you a little bit of an idea that there's an interesting interplay between the symmetry of a problem and the topology. Now, so the most important consequence of this, of having these two different topological phases, is to ask the question: what happens if you have an interface between the two? Okay, and so this is another sort of old problem in physics, and this is a problem that has been discovered and rediscovered many times over the years. And the idea is that if you have an interface between two different topological regions, on that interface you have sort of low energy states. Okay, so in this case, at the interface between the A and the B, you get a mode that is at zero energy. Now this is actually very easy to understand if you think in terms of this picture and imagine that these bonds are really strong and these bonds are really weak. Okay? Because if these bonds are really strong, then these are all sort of paired off, and then there's a state that's just left by itself, which is going to be at zero energy. Okay? Now, so that's a picture in the very strong coupling limit. Then you can ask, well, what happens if I weaken the coupling? But the point is, though, is that, you know, if we have this mirror image particle hole symmetry, then if the state is at zero, it has to stay at zero. It can't go anywhere, because if it moved away from zero, it would have to have a partner at a positive energy. So this state is really topologically protected. Even if you change the Hamilton, as long as you don't close the energy gap, this zero mode has to stay there. Okay? And so this is an example of what I like to call the bulk boundary correspondence. That if you have a topological classification of the bulk, and you have the boundary between two different topological states, you get these protected boundary modes. Yeah?
Those things have dynamics, those zero mode?
Well, it has zero energy, so yeah, no dynamics.
In this one.
So it sits at that one location?
Yeah, that's right. Yeah. So this is a phenomenon, I think, which was really first discovered by the field theorists. Okay, so Jaquib and Rebbe found this in certain studies of one-dimensional quantum field theories, and it was rediscovered by Sue Schrieffer and Eager, and then this is something which has come up over and over again over the years. Okay. Now, so this is sort of the first example of a topological, this bulk boundary correspondence, and what has emerged over the last several years is that there are many other examples of this. Okay, that it can occur in materials that people can do experiments on. Okay, and so this is really the story of topological insulators. Now, the first application of this idea in a sort of more general context was the quantum Hall effect, actually. Okay, and so in the quantum Hall effect, what you have electrons which are confined to a two-dimensional plane. Okay, and you put them in a strong perpendicular magnetic field. Okay, and you know what electrons like to do in a magnetic field? They like to go around in circles. Okay, and in quantum mechanics, when you have particles that go around in circles, it's kind of the same as electrons going around in an atom. So you get discrete quantum states. You quantize those orbitals, and the quantized orbitals for this circular motion are called Landau levels. And so what happens then is you can have a situation where you have these discrete Landau levels. You have some of them are filled with electrons, and then there's an energy gap to the next one. Okay, and so it kind of looks like an insulator. You have an energy gap separating the occupied electronic states from the empty electronic states. And so you might think it should be an insulator. But actually, it's not an insulator because if you apply an electric field, you know what happens when you have an electric field and a magnetic field, the cyclotron orbits start to drift. And so you get a current that flows perpendicular. Okay? And in fact, that current, if you measure it, it defines a Hall conductivity which is miraculously quantized to 1 part in a billion. Okay? And so what's going on here, though, is you do have an insulator, but it's an insulator with a non-trivial topological invariant. And so, so it was David Thales and his collaborators that realized that that if you have a two-dimensional insulator, if you will, that a two-dimensional insulator is characterized by another kind of topological invariant. It's not a winding number, but it's sort of like a winding number. It's called a Chern number. Okay? And when the Chern number is 0, you have an ordinary two-dimensional insulator. But when the Chern number is any other integer, you have an integer quantum Hall state, and the integer Chern number is exactly the integer you measure when you measure the quantized Hall height. Okay? So this is an example, sort of a topological insulator. Okay? Now, as I said, the most important consequence of this is what happens on the boundary. So if you have a boundary between a quantum Hall state with n equals 1 and, say, the vacuum, which is like a trivial insulator with n equals 0, then what happens, so this is actually, you get an edge state. And there's a simple picture for this if I think in terms of these classical cyclotron orbits. The electrons are going around in circles, but if there's a wall, then they sort of bounce off the wall. And then they execute this motion in one direction. Okay, so this edge state is sort of like a one-way street for the electrons. Okay? Now, if you solve this problem quantum mechanically, then what you find is that as a function of momentum, you have, there's going to be the bulk states of the valence band and the conduction band, but they're going to be connected by a band that crosses between the valence band and the conduction band. And this band describes electronic states that propagate only from left to right. Okay? And so we call these states chiral Dirac fermions. Okay? And so these chiral Dirac fermions are really remarkable things, because if you're a chiral Dirac fermion sitting on the edge, you have no choice but to move forward. Okay? There's no way you can move backwards. And so that means if you put in an electron over here, you know with 100% certainty it's going to make it to the other side. Okay? And it's this fact that is really sort of underlies this 1 part in a billion quantization that you measure in this perfect transmission of the chiral edge states is what's responsible for the experimental fact that you can measure this integer to 1 part in a billion. Okay? So you can't get rid of these states. So these boundary modes are something very special. Okay, so this is the quantum Hall effect. Of course, this was the physics of the 1980s. Okay? Now, the thing which happened over the last 5 or so years is the realization that there are more versions of this if you allow for new kinds of symmetries. Okay? And in particular, you see, because one thing, if you want to have the quantum Hall effect, you need a magnetic field which violates time reversal symmetry. Now, so what if you don't have a magnetic field and you do have time reversal symmetry? You can't get the quantum Hall state, but you can ask, is there anything you can get? Okay? And so this is where the story of topological insulators enters the game. And so it turns out that if you have a time reversal invariant insulator in 2 or 3 dimensions, then it turns out there are topological classes for those. And this is a new, and they are distinguished by a new kind of topological invariant. It's not a winding number, it's not a Chern number, and it's not even an integer. It's something which can either be 0 or 1. And so we call this a Z2 topological invariant. So the 0 is just a plain, ordinary, trivial insulator, but the 1 is a topological insulator. And in a topological insulator, what happens is you have an edge state. In a 2-dimensional topological insulator, you have an edge state. And the way you can think about that edge state is you can think about it as just like the edge state for the quantum Hall effect, except you have 2 copies. You have a right-moving one for the up spins and a left-moving one for the down spins. Okay? And this edge state provided you have time reversal symmetry, is something you can't get rid of, in the same way you can't get rid of the chiral edge state in the quantum Hall effect. So this is an example of something that's new, and so this state was proposed theoretically first, and then within a year or two, it was realized that one way you could make these is in mercury cadmium telluride quantum wells, and Lawrence Molenkamp and his group sort of did experiments on these two-dimensional mercury cadmium telluride quantum well structures, and were able to observe these conducting edge states. Okay, and so this sort of went from a theoretical idea to an experimental reality remarkably quickly. So you can do it in 2 dimensions. You can also do it in 3 dimensions. If you have a 3-dimensional crystal, which is time reversal invariant, there are also 2 kinds of insulators that you can have. Okay? And in a 3-dimensional one, you have a surface now, which is a 2-dimensional surface. And on the surface of a 3-dimensional topological insulator, you have very special surface states which have a Dirac type electronic dispersion. Okay? And so they have a conical energy as a function of momentum relation that reminds you of the energy momentum relation for a photon, or maybe for a massless relativistic particle. And so it turns out that there are a number of real materials that will do this. And so this is a picture of angle resolved photo emission data from Zahid Hassan from Princeton that shows almost a textbook perfect Dirac cone. So these 3-dimensional topological insulators are real materials that exist, and since these materials have been studied, there's been a whole flood of people worldwide studying all aspects of these materials. Okay, so this is the topological insulator. Let me just talk about one more example of this phenomenon. Yeah.
I was just wondering, in the previous case, the magnetic field made the electrons sort of hit the edge. And
Yes.
go around.
Yes.
With this quantum spin Hall insulator, what causes the?
Well, it's really the spin-orbit interaction, okay, which you can sort of think of as being like a magnetic field, but it's opposite for the upspins and for the downspins. Yeah, cool. Okay, good. All right. So this is, I'm sort of going through. I'm giving my usual whole colloquium in the first half of this colloquium, so I realize I'm going a little bit quick here, but I want to talk about one other phenomenon, which is the phenomenon of topological superconductivity. And so this is yet another example of this bulk boundary correspondence that I introduced to you. And so to think about a superconductor, the BCS model of a superconductor tells you that a superconductor is kind of like an insulator. Okay, so in the sense that it has an energy gap for its quasi-particle excitation. So a superconductor has a conduction band and a valence band separated by an energy gap in just the same way as an insulator. Okay, except for one qualification, which is so if you're going to view this superconductor as being like an insulator, it has a intrinsic particle-hole symmetry. Okay, which means that the conduction band and the valence band are exactly mirror images of each other. They're sort of redundant. So the structure of the conduction band determines the structure of the valence band. Okay, and so this adds a new twist to the topological problem. So instead of having time reversal symmetry, we have a new kind of symmetry, which is this particle-hole symmetry. So you can ask, well, given that symmetry, what are the kinds of topological classes that you might have? Okay? And the simplest kind of topological superconductor is actually a superconductor in one dimension. Okay? So if you have a one-dimensional superconductor, then, if you think about the boundary, you can think, well, what happens at the end? Okay? And so at the end of a one-dimensional system with an energy gap, there might be discrete states that have energy sort of within the energy gap. Okay, and those states, of course, are going to decay exponentially into the bulk. Okay, but there'll be end states. Now, because of this intrinsic particle-hole symmetry, if there's a state at positive energy, then there has to be a corresponding state at negative energy. Okay, unless there's a state at exactly zero energy. Now, if there's a state at exactly zero energy, it can't get away from zero energy. because if it tried to move away, then it would have to, you know, poof, a partner would have to appear out of nowhere. Okay? So these zero energy states, if they're there, are topologically protected. Okay? And they are precisely there if at the end of a topological superconductor. So it turns out there are two kinds of one-dimensional topological superconductors. They're the ones with the end states and the ones without. Okay? And so now these end states are very magical objects. Okay? And they're magical because I told you about this redundancy. You know, adding a particle up here is really the same state as removing a particle here. And so that means that adding a particle at zero energy is the same as removing the particle at zero energy. So that means that this particle, this zero energy quasi-particle, is its own antiparticle. Okay, so two of them, poof, they disappear. Okay, and so that is a Majorana fermion. Okay, and so so again, you know, I could go on at length talking about Majorana fermions. So let me just say that if you can make these Majorana fermions, then there is a very exciting potential application to use these to store quantum information in a way that cannot be destroyed by decoherence. Yeah.
Just one question. In what sense is that a fermion? Does it really have a spin?
You know, it doesn't have a spin, but you know, these operators anti-commute themselves, so it behaves everything, you know, like it should. Yeah. Okay. So then, you know, you can ask whether these things can exist in the real world, and so there's actually been in the last a year or so, there's been a very exciting experiment done at Delft University by Leo Kouwenhoven, and actually I understand that I think last week you had a visitor who talked about this experiment on a indium-antimonide quantum wire on top of a superconductor, and so the belief is that this should be a one-dimensional topological superconductor with these end states at the end. And so what they did is they tried to pass an electric current tunneling from a normal metal into this end here, and what they see as a function of the voltage is they see a peak in the current. Okay, and this peak, if you look at it with loving eyes, you will say that that peak is this Majorana zero energy state. Okay, and so this experiment might be the first observation of this sort of solid state Majorana fermion. The challenge for this experiment is to rule out all of the other less exciting possibilities for what the origin of this peak is. Okay, but this is certainly something that is stimulated a lot of interest in the community. Okay, so what I hope I've shown you is that this idea of the bulk boundary correspondence, you know, having a topological bulk defining defining these topologically protected boundary modes, is sort of a ubiquitous phenomenon. And so what I want to do now is I want to introduce to you a new class of problems that this idea can apply to. Okay, and so this class of problems, let me this is a much older class of problems than the sort of you know, quantum problems that I was talking about. So this goes back to Maxwell. Okay, and so Maxwell formulated the following question, which is to ask if you have a frame or a configuration, you know, of just masses connected by springs, you can ask, well, is that going to be mechanically stable? Okay, so if you were going to build a house like this, then, you know, you might worry that this might happen. Okay, right, and it would fall down. Okay, so what you have here is you have floppy modes. So this is like a zero frequency mode that you can have. Okay, and so what Maxwell pointed out is you can figure out how many of these modes you can have if you just count the number of degrees of freedom and the number of constraints. Okay, and if there are more, and so there are going to be, if you have ns sites in d dimensions, there are going to be d times ns degrees of freedom. And if there are n sub b bonds, then there will be that many constraints. Okay? And so the difference of those two gives you a lower bound for what the number of floppy modes is. Okay? Now, it's not an equality though. Okay? Now, so one thing you might do if you wanted to make sure that your house didn't fall down is you could put in sort of cross bonds, okay, and that makes this more mechanically stable, okay, and so then you have this difference becomes negative, okay, but of course the number of floppy modes can't be bigger than 0, okay. But one thing that you do when you do this is you introduce something new, which is called a state of self-stress. So what it's possible to do is to put these springs so that they are under tension or compression, okay? But there are no net forces on any of these, okay? So you can sort of, everything is balanced when you have this state of self-stress. So then you can ask, if you include these states of self-stress, what happens to this Maxwell counting rule? And so it can be generalized, and this is an idea due to Caledine, that if you include the states of self-stress, then the difference between the number of floppy modes and the number of states of self-stress is equal to this difference between the number of degrees of freedom and the number of constraints.
What is self-stress?
Self-stress is a configuration where the springs are under tension or compression. So there's a non-trivial tension in these springs, but there are no net forces on the sites. Okay, because you can see that on this site there are forces pushing down and to the left from the green springs, but there's a compensating force due to the red spring. So the forces all balance each other out. Okay, and so the number of states of self-stress are the number of independent ways you can do this.
And the forces, won't they just balance themselves out eventually because it'll move until the...
Well, no, but what I mean is they can balance themselves out with nothing moving. This is an equilibrium situation. It's not going to move.
Whereas before, you only had equilibria with no...
Right, exactly. So if I go back to here, so let's imagine it ends here. If for instance, if I put all three of these bonds under tension, then of course this thing is going to move in, right? So there are no states of self-stress in that. Okay.
Those equilibrium don't have to be stable.
Yes. Okay. So so this idea of thinking about the mechanical stability, of course, is an important and old, long-standing idea in engineering and architecture. You want to make sure your bridge doesn't fall down, or you might think about what would happen to the Hancock Tower if they didn't put the crossbars in, right? So this is an old and important problem. It's also a problem which can have applications in a number of different fields. And so now I have to confess, this slide is about stuff which really isn't my stuff. And I suspect there are people in the audience who know much more about this area than I do. But let me just say that, so one thing that is interesting to think about is the notion of an isostatic lattice. Okay? And what an isostatic lattice is it's a periodic structure. So I imagine something which is sort of periodically arranged, so it's periodic in space. So it's like a lattice, like a crystal, okay? But it is isostatic in the sense that the number of degrees of freedom exactly balances the number of bonds. Okay, and so in this sense, it's sort of on the verge of this mechanical instability. Okay? And so these isostatic lattices are sort of interesting things because they're on the verge of mechanical instability, and they can be applied to a number of different areas. So they can be model systems for a number of problems in soft matter and statistical physics. So for example, there's a problem of rigidity percolation. If you imagine a lattice where you sort of take springs out, at some point this thing is going to lose its mechanical rigidity. Okay? And at the point where that happens, you're in a situation where effectively, on the average at least, the system is isostatic. Okay? Another problem, this comes up in the discussions of jamming. So if you have like spheres that are packed together, if you imagine having them so they're just packed together at exactly the point at which it becomes jammed, again you have sort of an average isostatic. It's isostatic on the average. Okay, and so this periodic isostatic lattice is sort of a, a starting point for thinking about these more complicated systems. Okay, and so Tom Lubensky, my colleague at Penn, was interested in thinking about isostatic lattices for just these reasons, and he came up with the following sort of interesting observation. So what he was interested in was thinking about a Kagame lattice. So this is a I can think of masses and springs where the masses now are on the vertices of this Kagame lattice, which is has all these triangles in it. So every cross here there's a mass, and every line between them there's a spring. Okay, and the Kagame lattice, each site has 4 neighbors, and that means it's exactly isostatic. Okay, so it has just enough degrees of freedom, just enough. Okay, and so, but if you look at this isostatic, at this Kagame lattice, so the first thing to do is to imagine. Let's imagine that we have periodic boundary conditions, so that over here connects over here, and the top connects to the bottom. Okay, and so let's do the counting. So one thing you can see is that there's going to be a floppy mode that looks like this. Okay. And there's going to be a floppy mode that looks like this for every line of bonds that you could have. Okay? And so there's going to be a number of floppy modes that scales with the length of the system. Now, if you have periodic boundary conditions, you can also put every single one of these bonds, since it goes all the way around, you can put them under tension or compression. Okay? And so each line of bonds defines for you a state of self-stress. Okay? And so likewise, the number of those is going to scale with the number of lines. So the number of floppy modes is equal to the number of states of self-stress. And that makes sense because Maxwell's counting rule, so in the periodic system, there are exactly twice as many sites as there are bonds. And so that says that the number of floppy modes has to be equal to the number of states of self-stress. Okay? And so that sort of works out. Okay? Now, you can ask yourself then, what happens if I cut this lattice open so that it's not periodic anymore, but it has open boundary conditions? Now, in order to do that, I have to cut some bonds. I have to take some bonds out. So I've altered the balance between the number of sites and the number of bonds. Okay? And what you can also see is that I've gotten rid of these states of self-stress, because now if I put all these bonds under tension, then the ones at the end are going to move. Okay? So basically what you do is you kill the states of self-stress, but you keep the floppy modes. Okay? And the balance of bonds and sites still works. Now, what Tom realized is that something very interesting happens if you just rotate the triangles. Okay? So if you rotate, so I'm going to each triangle I'm going to rotate the down pointing triangles clockwise and the up pointing triangles counterclockwise, and so I end up with a twisted Kagame lattice. Okay? And in this twisted Kagame lattice, you can see that in the periodic case, I've gotten rid of all the states of self-stress. Okay? Because now if I put this line under tension, then there's going to be a net force on each site. Okay, so it's no longer a state of self-stress. You also get rid of all the floppy modes. Okay, so in the periodic boundary condition, it all makes sense. So you still satisfy the condition that the number of floppy modes is equal to the number of states of self-stress, but they're both equal to 0. Okay, the interesting thing is what happens if you cut it open. Okay? Because if you cut it open, again, you've cut bonds. So you've changed the balance. Okay? There aren't any states of self-stress to take away. So you had to add floppy modes. Okay? But where could those floppy modes be? Well, they didn't exist in the periodic system. Those floppy modes have to be localized at the boundary. Okay? And so this is what Tom realized. Okay? And so you can look at these floppy modes. So you can imagine, so now I have a strip, okay? And so let me just fix it on the top. So I nail these sites down on the top, and I have a free boundary on the bottom, and then there's going to be a floppy mode where they're sort of going like this, okay? And I can analyze this by solving for the normal modes of this configuration as a function of wave vector in the x direction. And so what you see in this picture is you see so these these are the acoustic modes here, okay, the long wavelength k equals 0 acoustic modes. But then here you see this mode at 0, okay, at 0 energy, and this is a localized boundary mode that is localized to this edge, okay, and so Tom Lubensky and his collaborators sort of realized that this was something which was new and kind of interesting. Okay, and so Tom, his office is down the hall from mine, and so he came up to me and he asked me, so are my boundary modes like your boundary modes? And my first response, so this is a year and a half ago, I said, no, Tom, look, you're doing classical physics. I'm doing quantum physics. There's no connection at all, so forget it. But Tom is he's a persistent guy, and so he came back to me and he said, are you sure? And so I tried to explain to him why it was that I thought they were different. And so I came up with the following argument. So look, so my problem is the Schrodinger equation. So the Schrodinger equation is a first order equation in time, okay? And so I'm interested in the eigenvalues of the Hamiltonian. And the eigenvalues of the Hamiltonian, they can either be positive or negative. I have a conduction band and a valence band, okay? And really it's the valence band which has the topological classification. So that's my problem. Whereas Tom's problem, Newton's laws are second order in time, okay? And so what he's interested in is the eigenvalues of this, which is called the dynamical matrix. And this is something which is guaranteed to only have positive eigenvalues, right? And so there's no valence band. Okay, so these problems are completely different, okay? But when I said it in this way, I was reminded of a story. And the story is the story of the legendary Solvay conference in 1927. And so this was a meeting that brought together the pioneers of quantum theory to discuss their most recent developments. And in particular, the famous venerable Niels Bohr was there. And the story goes that he bumps into the young and not yet quite so famous Paul Dirac, and asks him what he's up to. And so Dirac was a man of notoriously few words. And so he replied, I'm trying to take the square root of something. So Bohr said, okay, work on that. So now, we now know that the square root that Dirac was trying to take is probably the most consequential square root in the history of physics. Because the square root that Dirac took gave him the Dirac equation, okay? And so what Dirac was trying to do was to take the square root of the Klein-Gordon equation, okay? And what he realized, so how do you take the square root of this without taking a square root? What you do is you do this, okay? And so what Dirac's square root accomplished, in addition to explaining the origin of spin, Dirac's square root predicted that electrons have a valence band. Okay? He predicted the existence of the antiparticle of the electron, the positron. Okay? So he started with a problem that didn't have a valence band, the Klein-Gordon equation. He took the square root and he got a valence band. So I thought to myself, if I could just take the square root of the dynamical matrix, then I'd have it made. Okay? And so I went home and slept on this and realized that you can take the square root of the dynamical matrix. Now, this is a little bit of a technical slide and it's late, so I apologize for that. But let me try to take you through just a little bit of of how this works, because it's kind of cool. So, so how can you take the square root of the dynamical matrix? So the important thing here is that the dynamical matrix actually has some structure to it, because we're talking about a system of masses and springs. So the way you can think about the dynamical matrix is that if I think of the energy as a function of the displacements, then you get a quadratic energy, and the dynamical matrix is the quadratic form in that quadratic energy. Okay? But really what you're doing is you're stretching springs. So the elastic energy is really just the sum of 1/2 kx squared for all of the bonds, for the amount that I've stretched each of the bonds. And the amount that I've stretched each bond by is related to the displacements of each of the sites. Okay, so there's a matrix, which is called the dynamical matrix, that relates the displacement, the x and y components of the displacements of each site, to the amount that I stretch each bond by. Okay, and so this dynamical matrix sort of plays a fundamental role. It's the same matrix that relates the tensions in each bond to the net force on each site. Okay, so but given this dynamical matrix, you can just plug in E for in terms of U, and you can see that the dynamical matrix is Q transpose Q. Okay, so there's sort of a sense in which Q is sort of like the square root, but it's not quite the square root because it's not Q squared, it's Q transpose Q. Okay, so we're not quite to the square root yet. But Q transpose Q, if you have a Hamiltonian that is Q transpose Q, then this lights up another bell in my mind, which is supersymmetry. Okay, so Q transpose Q, this looks like supersymmetric quantum mechanics. Q transpose Q has a partner, which is Q transpose. Okay, and it's not too hard to see that any eigenstate of Q, Q transpose Q, I can get a corresponding eigenstate of Q transpose that has exactly the same eigenvalue. Okay, at least for the non-zero eigenvalues. Okay, so these two sort of objects have the same spectrum except for the zero modes. The zero modes, so the zero modes of D are the floppy modes. Okay, they're the things where Q, they're the U's that I can have that don't give me any E's, that don't stretch any bonds. Okay. On the other hand, the zero modes of Q transpose, those are the states of self-stress. Okay, so we have two different kinds of zero modes. We have the floppy modes and the states of self-stress. Okay, and so now, if we think about the two of these combined, then I can take the square root. If I combine the D and the D twiddle into a bigger matrix, sort of like Dirac, then this is a perfect square. It is the square of this. Okay, and so now this has a valence gauge. Okay, and in fact, this I can think of as being like a quantum Hamiltonian. Okay, and so I can use all of the things that I knew before about topologically classifying quantum Hamiltonians. I can now export that knowledge to this problem. And in particular, you can think about the symmetries. The symmetries of this problem, it has a time reversal symmetry. It also has a particle hole symmetry. So it's sort of like a combination of the topological insulator problem and the topological superconductor problem. And so this is a symmetry class that has a name. So if there are any aficionados in the audience, it's class BD1. It's the same symmetry class, actually, that the Sushri-Verheugen model is in. Okay? And so, so just by saying it in this way, I know exactly what the topological classes are. It turns out there are integer topological invariants. Okay, and so so given those, so now that I know that this effective Hamiltonian that I got when I took the square root of the dynamical matrix has some topological structure, it turns out in 2 dimensions there are actually 2 integer topological invariants. Okay, and I can think of those 2 integers as combining together to define a lattice vector. Okay. So then I went back and I asked, well, what's the topological class of Tom's twisted Kagame state? Okay? And it turned out actually that was 0. That's sort of the trivial state. Okay? But this suggested that there should be also some non-trivial states. Okay? And so we realized that we could change the twisted Kagame and deform it even more. And so rather than just rotating the triangles, I can change the shapes of the triangles and make a deformed Kagame lattice. Okay? And this lattice, if I think about this, the topological invariant of this are non-zero. Okay? And so then you can ask the question, so I have an interface between two different topological states. There should be zero modes on the boundary. There should be something protected on the boundary. Okay? And it's interesting, you can see, so if you solve this problem, what you find is that on one of the interfaces, you get a floppy mode. Okay? And so this is the spectrum of the Hamiltonian. So notice now it has a valence band, it has a positive energy and negative energy states. But of course it's mirror symmetric. Okay? It has this particle hole symmetry. Okay? And it has two sets of zero modes. One of them is a floppy mode, which is localized on this boundary, and the other one is a state of self-stress, which is localized on this boundary. Okay? And so, so these sort of go together. Okay. So now, this is a little bit different from the zero modes that Tom discovered. Right? Because remember, the zero modes that Tom Lubensky discovered were on the boundary, were on the edge of the system. Okay? And they were there because there was a mismatch between the number of bonds and the number of sites. Okay? Whereas here, this is exactly isostatic. There's no, I could put this on periodic boundary conditions, and the number of sites is exactly twice the number of bonds, and the number of zero modes is exactly equal to the number of states of self-stress, but somehow they're spatially separated from each other. Okay? So this is sort of different than Tom's zero modes. Okay? And so I asked myself the question, is there any way I can unify them and talk about them both at the same time? Okay? And in order to do this, what I realized is I needed to generalize this Maxwell's counting rule. Okay? And in doing so, what we were able to do is to turn it into actually a famous old math problem. So there's a very famous theorem in mathematics that goes under the name of index theorems. Okay? The Atiyah-Singer index theorem. And so this theorem is a version of that. And basically what it does is the following. So it takes, remember, Maxwell's counting rule relates the difference between the number of floppy modes and the number of states of self-stress, but it's talking about the entire system as globally. Okay? So we can ask another problem is we can ask, what are the number of zero modes and the number of states of self-stress in some subregion of a larger system? Okay? And so what we were able to prove is that this zero mode count has two contributions. It has one contribution which comes from the sort of balance of the number of sites and bonds inside this region. And it has another topological contribution that comes from looking at the topological state, the topological invariant on the boundary of this region. Okay? And so this formulation of the problem then is able to explain both the number of zero modes on the edge of the system and the number of zero modes at a domain 1. Okay? And so on the edge of the system, we can look at different kinds of edges, and I think I'm just going to finish up here. And each of these different kinds of edges has a different, zero mode spectrum, and those can be predicted by understanding the sort of both the local count of the number of sites and bonds on the edge, and understanding the bulk topological invariant. Okay, so let me just finish up now and conclude. And so the main point is that there's something common to both of these problems, which is sort of there's this very elegant mathematical structure, that tells you about the correspondence between some sort of bulk phenomena and a boundary and protected boundary limits. Okay, and so I've shown you that this is shows up in these topological electronic phases, which are the subject of a great deal of excitement in the hard condensed matter community these days, and they also show up in these mechanical modes of isostatic, classical mechanical systems. And so, so there's a lot more to do. All the analysis that we've done up until now has been about periodic clean systems. Okay. Now, in the electronic game, we understand that this topological classification actually can also be applied to disordered systems. Okay. And so there's nothing that says that a system has to be periodic in order to have a topological phase. Okay. And so there's an interesting problem is to talk about the disordered version of these isostatic lattices, and maybe that can be related to problems in jamming and things like that. Okay, are there other kinds of other versions of this problem that one might be able to do experiments on? So that's an interesting question. And then of course there's the question of interactions and nonlinearities, which may lead to interesting physics as well. Okay, so I think that's enough. So thank you very much.
Supersymmetric theories, often you have discrete symmetries or finite symmetry groups, and then you can define other indices, twisted indices, right, where you take traces graded by elements of this group. So this system, have you thought about systems where you have some extra discrete symmetry?
No, I haven't. Yeah, and I have to confess, my understanding of supersymmetry is not much deeper than what I showed you on the slides here. So there could very well be more interesting things to think about that I haven't.
I think in the case in which you are unlocking the index is 0, but you may still have topological invariance.
Well, that's very interesting, because you see, so one thing I'll say is, so this index that we have, it only tells us about the difference of these. Okay, so one question you might ask is whether there's some better, some stronger statement one can make about these two quantities. Independent of each other. So maybe there's something like that.
All that I've been discussing is when you combine an S-wave superconductor with your topological insulator.
Yes.
Is the topological insulator an S-wave superconductor?
Yes. I mean, though it's a little bit of a question of terminology, because S-wave, if you're classifying the Cooper pairs according to their rotational symmetry, you're breaking the rotational symmetry. But it's certainly the case that the order parameter is singlet pairing. Well, it's not even really singlet because you're breaking spin rotation. The spin orbit interaction breaks the spin rotation, but you're still pairing up and down. You're pairing an up spin at k with a down spin at minus k. That's what you're pairing. So in that sense, it is exactly like an S-wave superconductor. And so, but the thing I certainly can say is that if you have an S-wave superconductor, it will proximity couple to it will induce superconductivity in the surface state. Okay, there's no, that does not violate any symmetries that are present.
Well, this is kind of a silly question, but relating boundaries and bulks is, of course, all the rage in string theory and
Of course.
ABF, etc.
Yes.
Is this related?
Yeah, I think it is. I mean, I say that, knowing epsilon about those fields, but no, but to
I know
the extent of my
square.
okay.
I'm better than you.
But yes, I do believe they are exactly the same type of phenomenon. Yes.
So this mechanical modes on the surface, should we conclude that something funny happens on the surfaces of crystals? Because these lattices are models of crystals.
Yeah, that's right. No, but they're very special models of crystals. Okay, so these lattice models are central force spring. They're lattice points connected by central force springs. Now, in reality, if you wanted to have a spring model of a lattice, there are going to be a lot more springs. Okay, there's going to be springs connecting the first neighbors, and there's also springs in the second neighbors, and they're going to be long springs. It's just they're weaker. Okay, and so to that extent, then if I have many more bonds than I have sites, and so it's never going to be the isostatic limit. Okay, so it's really in this sort of specialized. So if you have a crystal where it's a really good approximation to only have the first, to have some.
But as you said, there are no such things, probably.
Well, so, I mean, certainly you can make them, out of, if you have hard spheres, then it's a good approximation that you're not having further neighbor interactions. So I think, for problems in sort of soft matter, it is a relevant thing to consider. And so if you want to apply it to actually a crystal material, then you have to ask yourself the question whether that's a good approximation.
But in fact, your soft model was just balls and springs.
Yes.
So has anybody made it? I mean, you can just make it, right? The two-dimensional version.
Sure, one could. Yeah, I don't think anybody.
Nobody's done? It doesn't look that big.
Yeah.
Right?
Maybe you should buy a kit.
Yeah. Actually, so I have it. So I know how to make the centrifugal heater valve.
Uh-huh.
I can tell you that.
Okay. 1D. that's
Yeah,
it.
1D. Yeah, you can make the centrifugal heater valve. Yeah.
So in a way, aren't the self-stress are sort of over-constrained?
Yes.
And the floppy modes are under-constrained?
Exactly.
Yeah.
Yes, that's exactly it. Yeah. But you see, the beauty thing is that this difference between the number of states of self-stress and the number of floppy modes is really it's a topological index. Okay, and so this fancy mathematics sort of applies to that.
So when you say topological, could you sort of sum it up over the whole thing and you get a number, a single number?
Yeah. Well, what I'm saying is that this index is so this difference is an index which is related to a topological property of the bulk, and that's the content of this index there.
Okay, let's thank Shirley again. And